Hello, student.
Okay. Other locations. So, and
Hello, student. Hello everyone, welcome to my channel. This is Karuna teaching the course Computer Architecture and Organization. Fourth unit contains the following topic, out of which in this video we are concentrating on handling multiple IO devices. Let us see how processor will handle multiple IO devices. Here multiple IO devices may be connected to the processor and the memory through a bus. These devices may be capable of generating interrupt requests. Suppose device X may request an interrupt while device Y being served, or several devices may request interrupts at the same time. This gives rise to a number of questions. How can the processor recognize which device requesting an interrupt? Each device has its own ISR. Each ISR is having its own address. How can the processor obtain the starting address of the appropriate interrupt service routine? In each case, here ISR, full form of ISR is interrupt service routine. Next question, should a device be allowed to interrupt the processor while another interrupt being serviced? Coming to the next question, how should two or more simultaneous interrupt requests be?
On PCs request the interrupts at the same point of time, then there the problem arises.
handled by the processor. Let us see the solutions for all these questions, or we can say all these questions can be solved by polling mechanism, vectored interrupts, interrupt nesting, daisy chain scheme, arrangement of priority groups. Let us see one by one. So, the way of approach for solving these problems vary from one computer to another. Here, this is the previous topics diagram.
लेकिन ये टॉपिक बहुत इंपॉर्टेंट है आपके कॉम्पिटिटिव एग्जाम्स, कॉलेज यूनिवर्सिटी एग्जाम में। तो इसको मैं बहुत ही इजी तरीके से विद एग्जांपल्स जो है वो आपको एक्सप्लेन करूंगा। तो गाइस फटाफट से वीडियो को लाइक कर दें, चैनल को सब्सक्राइब करें अगर अभी तक आपने नहीं किया, और अगर कर भी दिया तो और डिवाइसेस से सब्सक्राइब करवा सकते हो, सब्सक्राइबर्स बहुत जरूरी हैं। तो चलिए स्टार्ट करते हैं। व्हाट इज द कॉन्सेप्ट ऑफ इंटरप्ट? तो इंटरप्ट
time during your class that some of the student in the class has interrupted the particular teacher or particular faculty. Okay, what is the meaning of interrupt? Interrupt is nothing but disturbance, or we can simply call it as abnormal termination, or we can call it as some nuisance. Something which is not properly terminated is an interrupt. Okay, now why we are able to listen this topic now in our computer organization subject? Sir, why there is a disturbance type of topic in CO subject, whether it is for the good sake of system? My dear students, whatever the topics we will discuss in computer organization, they are all part of only one requirement, that is how we can able to develop computers with good performance, how we can improve the performance of our computers, and at the same time how we can remove the drawbacks of our system. So with that sense we can able to guess that interrupts is also one of the added advantage of our systems. So what is an interrupt? Okay, why our computer will make use of this interrupt topic, and who will use these interrupts, and what are the advantages? Each and everything I am going to clarify in my today's video. Okay, my dear students, let me tell you one scenario first, then I can able to explain this interrupts with the help of one example so that it will be clear to you. Let us say this is our processor, and here there is one output device, that is a printer. Okay, and this is a user. Okay, this is a user, this is our processor, and this is our printer. Output device, processor, user. So for our simplicity, I have taken only these three diagrams. Now let us say user want to take out some prints of pages. Let us say user want to take out 100 pages of print. How many? 100 pages at a time user has given the print command. With the help of print command, user has given the prints. Now first the request will go to the processor. Okay. Now with the help of processor permission only, the control will go to the printer output device. Now this 100 pages command will go to the printer, and you know that printer cannot print those 100 pages within 30 seconds or 1 minute. It is a matter of some duration. Yes or no? Depending on the printer speed, let us take this printer will take to print this 100 pages 5 minutes. How long it will take? 5 minutes to print all those 100 pages. Okay. Now what happened when the printer is printing those 100 pages in the duration of 5 minutes? During this 5 minutes time, our processor will be idle. It will be very free, which means it won't have any other work to do. Simply it will be concentrating on when this 100 pages is going to finish out. Okay, yes or no? Meanwhile, there will be some other device which wants the request of the processor, which wants the service to be fulfilled by the processor. So what we can do now in this situation? We want to utilize our processor, but our processor is very idle. It is waiting for the 100 pages to get print. Already this work is going on. So what we can do means, let us say there is one more device, device 2. This device 2 also wants the request of this processor. At this time, what this device 2 can do means, device 2 can send one signal which is known as interrupt. It is a hardware generated signal. What signal it will send? Device 2 will send the signal directly to the processor. Yes, dear processor, I am ready to fulfill the request. Okay, my request is there, please fulfill my request. I am ready to do this work. I am ready for this work, please fulfill my request. Please give the permission. Then once the processor will get this signal, processor can fulfill the device 2 request also. So hopefully the concept of interrupt has been clear to you. Why this interrupt is used? Interrupt is a hardware signal which is generated by the devices. When they are going to generate this interrupts, whenever processor needs to fulfill the request, they will send this interrupt signal to the processor so that processor can fulfill their request. Okay, this is the purpose of interrupt. Why we are using the word interrupt? You know, already processor is doing this work. What is that 100 pages print? Even though device 2 has interrupted. Device 2 has interrupted the processor for good sake only. Processor is idle, only it is observing this 100, when this 100 pages is going to print out, when these 100 pages are going to be printed. So meanwhile, processor will fulfill the request of device 2. Similarly, it may happen for device 3, device 4 and so on. So what is a interrupt? An interrupt is a hardware signal. Who will generate this interrupt? Interrupts are generally generated by the devices who want to fulfill the request. And to whom the interrupts will be sent? Interrupts always will be sent to the processor, so that processor can fulfill the request. Okay, clear? Now let me take one more example to you to give the clear idea. So if you want, you can take down this diagram. See, simply pause the video and you can take the diagram. Okay, the good thing about online video lectures is we will save lot of time. Okay, students will save lot of time, a lecturer also will save lot of time. Yes or no? The reason behind this is because simply you can pause the video. There is no need for me to give separately, take 5 minutes and note down the or take the diagram. Yes or no? That is one of the big advantage of online lecture videos. Okay, anyhow, so interrupts. Now let me take one more example. Let us consider there are two programs, program 1 and this is program number 2. So this program 1 want to do this work. Which work? Compute work. Program 2 want to do this work, print. Compute program is responsible for producing lines of text. Some lines of text it will produce. Print program is responsible to print those lines of text. So One program, compute, is responsible to generate the lines of text. Print program is responsible for producing the output. Clear? Now, let us say compute program has generated 2 lines of text. Once it will generate 2 lines of text, it will be idle. 2 lines of text is ready. Now these 2 lines of text is ready to be printed. So what our print program should do means it should display these 2 lines at a time simultaneously. Okay, now once it will display these 2 lines, again it will wait. Yes or no? During this waiting period, what our compute program should do means it should generate these 2 lines of text. Once it will generate these 2 lines of text, again it will go in waiting stage. During this waiting stage, print program should print these lines of text. Which means you got one clear picture here. When processor is busy in compute text, then what happened? When the processor is waiting, it don't have any work, during this time the print program should utilize the process. When the print program is idle, when it is not doing any work, the compute program should utilize the process. When compute program is free, when it is not utilizing the processor, then print program should utilize the processor. Which means if one program is not utilizing the processor, immediately the other program should send the interrupt to the processor, and it should take the permission from the processor and should fulfill its request. That is the main purpose. That's why we have taken this example, compute and print. If you want, you can take one more program number 3, which can do some other work. The main purpose of interrupts is the processor's idle time will be reduced with the help of interrupts. How the processor's idle time will be reduced? Because of interrupts. If one device is ready to get serviced, immediately it will send the interrupt to processor, so that processor can fulfill the request of that device. Okay, so hopefully the concept of interrupts has been clear to you. So with this, let me close my today's session of video on interrupts. See you soon everybody. Take care. Allah Hafiz. What is the meaning of access the data? Computer is having directly will take it from the cache memory itself. That is the big
all grounded, and if all the switches are closed, a bus line, we call it as interrupt request line, to communicate to the processor. This bus, the next topic is interrupt hardware. Normally interrupt signal make use of a bus line, we call it as interrupt request line, to communicate to the processor. This bus interrupt request line uses switch grounds. See here in this diagram, these are all the switches. Okay, they are all grounded, and if all the switches are closed, then the interrupt request signal will be processed to the processor through this interrupt request line. When it is open, then the voltage on this line is VDD. When the switches are closed, that means they are grounded, the voltage will be dropped to 0. This is the hardware that works for interrupt signal. So this interrupt signal is the combination of all interrupt signals generated by the switches.
Good morning, students. I welcome you all for another lecture on the course Computer Architecture and Organization. In today's class, I am going to discuss about the concept interrupts. So first, what is meant by an interrupt? Idea in this case, the information of this. So if you what all is fine. And next important thing is how our CPU logic level present on this INTR bar is equal to 1. You remember, friends, our processor regularly verifies the logic level on this INTR. It verifies the logic level of INTR bar only when before starting of every instruction. That means after execution of every instruction, before one start the next one, it will go and verify the logic level present on INTR. So here only one device send a request, it easily identifies only that device send a request. If you have multiple devices send a request signal, then how your CPU can recognize which device send it request. But one thing you have to remember, friends, that is whenever a device get a service from the processor, or whenever the device get a response from the processor, that means once your processor going to provide a service for any request, it issues acknowledgement signal. Once a device receives that acknowledgement signal, then and
not based on the First Blood. First Blood. Respawn. First Blood.
हेलो दोस्तों, गेट्स मैसेज में आपका स्वागत है। इस वीडियो में हम डिस्कस 1 यानी एवरी क्लॉक हजार्ड्स इन पाइपलाइनिंग होते क्या लेते वो हम वाइप जैसे से देखना I1 अभी तक एग्जीक्यूट नहीं हुई।
memory for delayed code execute and write, and you can see these the set of clock cycles. Now F1 has executed normally. F1 has successfully completed this step. Fetching of instruction 1 has completed. Now during the fetching of second instruction there will be a completed. 2 will first delay will happen in the availability of instruction, and I am going to give an example also to you so that you can get clarity and difference between them. So let us start our today's. If fetch unit will fetch 2 itself, instruction 2 will be fetched, and then instruction 2 will be executed in cycle 3. Now what happened, you know, next step, let us say one more instruction is there, I3 execution.
Let us talk about micro-programmed control unit. So generally in micro-programmed control unit, we will be writing some code, I can say, okay. It's not a circuit. So I can say that we will be storing the control signals in a memory, remember it. It's all about control signals. Finally, you remember one thing, control unit should generate control signals for, you know, for making your circuits work, right? Control signals. That control signals can be generated using circuit that is nothing but hardwired, right? If you use circuit, then it is called hardwired control signals. Second one, we have micro-programmed control signals. We can program them. Sir, why we have to program? For what kind of instructions we have to do micro-programmed control unit? We will see. Especially for RISC kind of architectures, people prefer hardwired control unit because it is simple to design. But when the instructions are CISC instructions, then the number of control signals, otherwise the complexity will be increased. That's why generally we don't design hardwired control unit. Rather than that, we go for micro-programmed control unit. In that, we will be storing the control signals in a memory. That is the idea. Now we'll see how that idea will work. So especially in CISC kind of instruction sets, the number of operations are highly variable. We can't divide the work into 5 parts. So some instructions might take 5 units, some instructions might take 10 units, some instructions might take 7 units. Example, see this instruction, a simple instruction, add R1, R2, R3. So it is a RISC kind of instruction, right? So that's why it takes only 5 stages. Correct? We can design a 5-stage system. But When you have this kind of instruction, add memory of 100, memory of 200, imagine this kind of instruction, memory of 300. Really this, what is the meaning of this instruction is easily we can predict. Go to memory of 200, okay, go to memory of 300 and fetch the operands, right, x, let's say y, then add them, okay, we need adder circuit, x plus y, then store it in memory of 100. How complex this instruction is, to execute it you need lot of cycles, correct? So this kind of instructions are generally called CISC instructions. Then you might require more than 5 stages to execute this instruction, correct? Now that's why for this kind of model generally people use, it will be very difficult because that is what experience says. So according to experience people realize that, so for this kind of CISC kind of instructions, micro programmed control unit will be better, where we will be storing the control signals using the memory. That means we are programming the control signals. We are not, creating the circuit for the signals. Okay, there are two models. Let me repeat again. We can generate control signals using circuit, that already we covered. Second thing is program it. So there will be a program which is going to generate the signals. Okay.
Microprogrammed control is an alternate to generating control signals by hardware. So in hardware, the signals were being generated by interpreting the contents from the instruction register and the timing signals from the step counter. But this microprogrammed control is a software approach. Here the signals are generated. Microprogrammed control is an alternate to generating control signals by hardware. So in hardware, the signals were being generated by interpreting the contents from the instruction register and the timing signals from the step counter. But this microprogrammed control is a software approach. Here the signals are generated in each step, which is determined by a program which is stored in a special memory. So this control program is known as the microprogram. And the memory on which it is stored, it is on the processor chip and it is known as the control store. In T2 stage, some control signals would be required and so on. So if it is a 5-stage organization, I would be having 5 stages and micro instruction control store. So suppose one given time in stage 4 or in any particular step, only one of the ALU operation would be set to high. So if the ALU operations were 16 in number and we were using 4 bits, we can use 4 bits to identify them. So add can be represented by 0000. Sub can be represented by 0001, because at any given point only one of the have been formed or memory data minimally encoded and multiple control signals. Microprogrammed control is an alternate to generating control signals by hardware. So in hardware, the signals were being generated by interpreting the contents from the instruction register and the timing signals from the step counter. But this microprogrammed control is a software approach. Here the signals are generated in each step, which is determined by a program which is stored in a microprogrammed control is an alternate to generating control signals by hardware. So in hardware, the signals were being generated by interpreting the contents from the instruction register and the timing signals from the step counter. But this microprogrammed control is a software approach. Here the signals are generated in each step, which is determined by a program which is stored in a special memory. So this control program is known as the microprogram. And the memory on which it is stored, it is on the processor chip and it is known as the control store. And control word is, this is another terminology which tells you that It is a word whose individual bits represent the control signals for each step in the sequence. We will go more into detail of this where it will be easier for you to understand. And the sequence of control words corresponding to the control sequence for a machine instruction. So this is called micro routine, and in the micro signal, so in hardware the signals were being generated by interpreting the control. Microprogrammed control is an alternate to generating control signals by hardware. To generating control signals by hardware. So in hardware the signals were being generated by interpreting the contents from the instruction register and the timing signals from the step counter. But this micro-programmed control is a software approach. Here the signals are generated in each step which is determined by a program which is stored in a special memory. So this control program is known as the micro program. And the memory on which it is stored, it is on the processor chip and it is known as the control store. And control word is, this is another terminology which tells you that it is a word whose individual bits represent the control signals for each step in the sequence. We will go more into detail of this where it will be easier for you to understand. And the sequence of control words corresponding to the control sequence for a machine instruction. So this is called micro routine, and in the micro routine, the individual control words are referred to as micro instructions, and all the micro routines for various machine instructions are stored onto the control store. Let us take a look at an example. Suppose I have an some instruction, say I1, which corresponds to say add, register, 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 and this, if I'm talking about a 5-stage organization, so this is having 5 stages wherein each step certain control signals are required. So in T1 stage, some control signals would be required. In T2 stage, some control signals would be required, and so on. I'm talking about corresponds to one which corresponds to, say, add, register, register, register. And this, if I'm talking about a 5-stage organization, so this is having 5 stages, wherein each step certain control signals are required. So in T1 stage, some control signals would be required. In T2 stage, some control signals would be required, and so on. So if it is a 5-stage organization, I would be having 5 stages, and in each stage certain control signals will be required. So for this execution of this machine instruction, this set of micro instructions will be stored in the control store, and each control word, so if suppose there were these many control signals, so the control word is like this. So this is the control word, and each bit is representing one control signal. So like this bit is representing PC in. That means whenever PC in is enabled, the system is able to write in contents into the program counter. So if it is 0, that means it is disabled. PC out is enabled, that means the program counter can be read. Similarly, if you see over here, we have MAR in, read, MDR out. So these are the enabling signals for the individual registers. There is a select for the multiplexer, an add signal which is for the ALU. ZIN and Z out are the enabling signals for the Z register of the ALU output, and so on. This is the WMFC, wait for MFC signal. This is the end signal, and so on. So if there were 5 stages, we would be having 5 micro instructions over here. As you can see, there are 7 micro instructions. Where in this particular implementation, 7 steps are being required for this particular instruction. That is the hardware implementation. Each control word over here, as you can see, each bit is representing a control signal. So this over here, each control word over here is called the micro instruction, and this whole set of micro instructions for a particular instruction, this is called the micro routine. And this micro routine is stored in the control store, which is a special memory. So all the micro routines for all the machine instructions will be stored in the control store. all the machine instructions will be stored in the control store. So here is the instruction register where a particular instruction will be, when it is fetched, it will be put in this instruction register. Depending upon what is the instruction, the starting address will be generated. This starting address will correspond to the control store. Will be. So here is the instruction register where a particular instruction will be, when it is fetched, it will be put in this instruction register. Depending upon what is the instruction, the starting address will be generated. This starting address will correspond to the address of the micro routine for this particular instruction. So if it is an add instruction, whatever was the starting address of the micro routine of the add instruction, that will be generated. It will point to that address in the control store. So suppose if this is the control store where all the micro routines are loaded. So suppose this was the micro routine for some instruction 1, this was the micro routine for some instruction 2, and so on. So this will generate the starting address. What store? So for some instruction 1, we will have a micro program counter to correspond to the micro instructions. So whatever is the address of the micro routine, that will be loaded in the micro program counter. This will also have inputs from the clock. So each micro instruction will be pointed to from the control store. That particular control word will be taken out, and depending upon that control word, whatever bits are high, those particular control signals will be generated. As soon as one control word has been executed or taken out, microprogram counter will be incremented by 1 to point to the next micro instruction. Once this is complete, once this micro routine is complete, that means that instruction, that particular machine instruction has completed its execution, and the next instruction fetch cycle will begin, and the next instruction will be brought into the instruction register. So if we have 1 bit for each control signal, this would require a very large control word. Another, and that is called a horizontal organization, where each control signal has a bit. It is seen that many of the signals are mutually exclusive. That means in one particular clock or in one particular stage of the sequence, one of those control signal would be high. Like for an example, the ALU functions. In any given time in stage 4 or in any particular step, only one of the ALU operation would be set to high. So if the ALU operations were 16 in number and we were using 4 bits, we can use 4 bits to identify them. So add signal has its own bit operation for memory address, which each control signal would have its own bit. And so higher operation, this is possible because we are allowing parallel use of resources, and